given two events, A and B, we can define a new event called the intersection of the events. And it's denoted by the symbol red A intersection B. So the event A intersection B is the event that A and B occur. And the outcomes in this event are all of the simple outcomes which occur in both of the events A and B. For example, suppose I roll a six-sided die and observe the number on the uppermost face. My sample space is the numbers 1 through 6. And if F is the event that I observe a number larger than 2, and O is the event that I observe an odd number, what's F intersection O? Well, here I've listed all of the outcomes in F and all of the outcomes in O. And the outcomes in F intersection O are the outcomes which are common to both. And these are highlighted in red. And we get F intersection O consists of 3 and 5 because those simple outcomes are in both F and O. Here's an example. In an experiment, we roll a fair six-sided die twice, observe the numbers on the uppermost face for each roll. And A is the event that we see a 6 on the first roll. B is the event that we see a 6 on the second roll. See if you can find A intersection B before I show you how. I'm going to highlight A in red and B in blue. You see there's one outcome which is common to both sets, and that's the outcome 6, 6, a pair of sixes, 6 on the first and 6 on the second. So therefore the probability of A intersection B is 1 over 36 because there's a single outcome in there. Conditional probability is something which is natural, but we need to develop the notation to go with it. So in a previous example, we estimated that LeBron James had a probability of getting a basket on his next attempt at field goal of 0.496. We used his career field goal percentage to estimate that. Now, we might have looked at the split statistics online on ESPN and seen that his field goal percentage varies from season to season. So instead of using his career field goal percentage, we might have used his field goal percentage for the current season, which is slightly different. It's 0.489. We also see that his field goal percentage after 2 days rest is slightly larger than his career field goal percentage. It's at 0.52 for the current season. So we see that this field goal percentage depends on some underlying conditions or factors. Now we might use this prior information to estimate his probability of making a field goal on his next attempt. So for example, we might estimate that the probability that he makes a field goal on his next attempt with his current season field goal percentage, or if we knew that his next attempt would be after 2 days rest, we might use the field goal percentage after 2 days rest for the current season. The actual calculation would be field goals made after 2 days rest divided by field goals attempted after 2 days rest, which results in 0.52. So we're using the prior information, taking it into account to make an estimate of probability. In this case, we're estimating a conditional probability given that the underlying conditions of the experiment for the next shot will be in the 2014-2015 season after 2 days rest. Notationally, if A and B are events in a sample space and the probability of B is not equal to 0, the conditional probability is denoted by this symbol at the end of this definition, and it's read the probability of A given B. This is the conditional probability that the event A will occur given that B has occurred or is guaranteed to occur. So if we know that B is bound to occur, we're calculating the probability of A, taking that into account, or under those conditions. The calculation of the probability of A given B in an equally likely sample space is very intuitive. We're going to look at an example, and I think you'll probably come up with the formula before I show it to you. Suppose I have 100 blue marbles and 100 red marbles in a box. And suppose I know that 75 of the red marbles have a tiny white dot, and the other 25 are solid red marbles. And now suppose I do the following experiment. I draw a marble at random from the box, and I let R be the event that the marble is red, and WD the event that the marble has one of these tiny white dots on it. Suppose now I draw a marble from this box, and I look at it, and without letting you see the marble, I give you some prior information. I tell you this is a red marble. And then I ask you, what's the probability that it has a white dot? Most likely you thought, or you said, that probability is 3 over 4. And if you think through what you did to arrive at that number, you probably said, okay, there were 100 red marbles in the box, and 75 of them had a white dot. I know you have one of those red marbles. Since 3 out of 4 have a white dot, the probability it has a white dot is 3 over 4. And this is the calculation you did. In summary, you took the number of things in the event WD intersection R, the number of marbles which were red and had a white dot, and divided that by the number of red marbles. And that's our formula. We could divide by the total number of elements in the sample space, which is 200, above and below, without changing this number. And we'll see that this number, 3 over 4, is also equal to the probability of WD intersection R divided by the probability of R. And that's our formula. If A and B are events in an equally likely sample space, we have the probability that A happens, given that B has already happened, is the number of things in A intersection B divided by the number of things in B, which is also equal to the probability of A intersection B divided by the probability of B. And that formula holds in general, whether it's an equally likely sample space or not. We have the conditional probability that A occurs, given that B has already occurred, is the probability of A intersection B divided by the probability of B. Let's calculate a few. Suppose I roll a fair six-sided die twice once again, and now I have 3 events. A is shown in red. It's the number on the event that the number on the first roll is a 6. B is the event, shown in blue, that the number on the second roll is a 6. And C is the event that the numbers resulting from the 2 rolls add to 11. What is the probability of B given A and the probability of C given A? You might want to try to calculate these before I do to see if you have the concept. Once again, I've highlighted the elements of A in red, the elements of B in blue, and the elements elements of C in orange. Now I'm going to apply the formulas. A intersection B has one outcome in there, pair of 6's, and A intersection C has the pair 6, 5. Now applying the formulas, the probability of B given A is the number of outcomes in A intersection B over the number of outcomes in A, which is exactly 1 over 6, and the probability of C given A is the number of outcomes in C intersection A, which is 1, divided by the number of outcomes in A, which is 6, so that's also 1 over 6.